This segment discusses the other source of t-values that go into conducting a t-test for one sample. Specifically, I want to go over the formula for what I refer to and what we will refer to as data-generated t-value, because this is the t-value that you will calculate using information about your sample as well as the population. And of course, the first several segments that you may have hopefully already watched discussed where the tabled t-value came from and how to select the correct tabled t-value. Those t-values in the t-table represent the amount, and this is, if this sounds familiar, what I'm about to say, it should sound familiar because we discussed this in some depth when we were going through confidence intervals. The t-values in the t-table, represent the amount, or the amount of standard error that you could expect to surround a mean given certain conditions. And what are those conditions? Your sample size, or degrees of freedom, and the task at hand. So in other words, given those conditions, the size of your sample and what you're trying to do, the t-table will show you how much standard error that you could reasonably expect would occur by chance. And that's a really key phrase to understand, that you could reasonably expect to occur by chance. That's a phrase that we are going to use for every single probability distribution that we work with. In the case of t measures units of standard error. So the t-values in the t-table represent the amount of standard error that you can expect to occur by chance given certain conditions. The conditions are sample size and the size of your critical region, or the task at hand. Those two things are saying the same thing. I hope that that's evident. Now, this is how many units of standard error, or how much standard error actually do separate two things. So this is data generated. The formula is pretty simple, and hopefully you're already pretty comfortable and confident in calculating the denominator for this formula. T, data generated T, again, see, data generated T, it's the T value that comes from your data. T equals your sample mean minus the given population mean. Think back to all those hypotheses that we went over, right? All those hypotheses that I used as examples to illustrate a t-test for one sample, all those hypotheses had a parameter included in them, right? Population mean equals. Well, the population mean is the given parameter, the assumed parameter. The given parameter, or the assumed parameter. So data generated t equals sample mean minus the given population mean. That difference gets divided by the standard error for the sample, which, by the way, is calculated exactly like it was calculated before. The standard deviation for the sample divided by the square root of n. That number, that amount, the standard error for the sample, gets placed in the denominator of the formula. So essentially what's going on here is that you are finding the actual raw mathematical difference between two things, a sample mean and an assumed parameter. You're just subtracting those two things and finding the actual literal mathematical difference between those two things. And then you are standardizing that difference by the standard error. You're finding the difference between two things, and then you are standardizing that difference by the standard error. Hence, data-generated t represents units of standard error, the actual amount of standard error that separates two things.